Hello everyone, we are group 7 and we are presenting our theme design project, which is fluoride level observation in drinking water. This is the inside of our device. So as you can see here, from this point we have our laser, we have our filter and our lens. In this square holding is the sample of our cuvette that has the rhodamine B and the fluoride concentration. We have our photodiode, and we have our ESP32 microcontroller that is attached and connected to our display. Okay, so as you can see here, our system says it's ready. This is connected through our Bluetooth device. So we have on our BLE connection a BLE server that's connected to our device, and we are allowed to connect it through our device to make sure that it says system ready, along with other commands that allows us to control our system portably. So now we will go in through our samples and show you what we will be testing. So as you can see here, we have 9 different samples. So we have 0.1, 0.0, 0.1, 0.5, 1 milligram, 5 milligram, 2 milligram, 7 milligram, 8, and 10 milligrams. So that consists of all of our samples.
We're going to send a message, a command to our monitor and / device to start the testing. Then press it, and then it will just start measuring.
So as you can see, our first sample inside of our device is 0.0 milligram per liter, and this is regular drinking water.
It's just distilled water.
Distilled water.
Yeah.
So within our device, our orange emitted light is hitting our photodetector, and it is gathering the correct fluorescence intensity, and right now it's showing up as 20.18. So now we will be opening up our device and changing out our 0.0 milligram per liter to our 0.1 milligram per liter sample.
Right.
And once again, with using our Bluetooth portable app, we will be able to take the next sample . And now it is showing that our fluorescence intensity is 19.86 for our 0.1 milligram per liter sample. Now we will change out our sample and calculate the next cuvette.
0.5.
We are putting in our...
I thought it was 0.2.
Now we will be calculating our 0.5 milligram per liter cuvette sample. And the lux value is 23.22 for our 0.5 milligram per liter sample. Now we will be calculating our next cuvette sample, which is our 1 milligram per liter.
Mm-hmm.
All right, now we have our next calculation, which is our lux showing 21.54. Now we will be testing our 2 milligram per liter sample. So for a 2 milligram per liter sample, our Lux is 21.02. Our next sample is our 5 milligram per liter cuvette. Okay, so we're measuring our 5 milligram per liter sample, and our current Lux value is 21.34. Now we are measuring our 7 milligram per liter sample. And for our 7 milligram per liter sample, it's showing as 21.82 for our Lux value. Our next sample is going to be 8 milligrams per liter. Okay, so for our updated 8 milligram per liter sample, our Lux value is showing 21.38. Okay, after our first initial testing that you guys saw, we did 2 more rounds of testing, and we were able to gather more results, and this allows for better perpetuity and consistency with our device.
Hello, this was the first iteration for the Group 7 PCB. Here, some of the issues that we ran into with the PCB to start off. One of the circuits that was actually controlling the chip PU was wired incorrectly, and that was causing a problem from resulted in the chip not being booted up. And so we had to go back and reroute a trace to a new resistor that's right here on R19 that allowed us to get in the extra trace that was needed so that the PCB could boot up. Not a known issue was the boost switching regulator that we used. That one was not working. One of the main known factor reason why it wasn't working was due to the MOSFET that we used was implemented incorrectly, in addition to the actual regulator itself had just issues when adding load to do testing. It just was not regulating the voltage correctly. Overall, every other component worked, and we were able to actually fully get the chip working in terms of like booting up the MCU. And to show a small demonstration here, we go over here to the laptop, and then we will be selecting the port. And then we'll be running just a small miniature code just to show that everything is working according to plan. So then now we have compiling, and I'm gonna press reset in the boot. I'm gonna hold boot down, and then we're gonna see what happens. And here you can see that we're able to successfully connect, which means that we're able to run code. Next order of business, we're gonna actually show the final PCB and all the changes that were made. So over here is the final PCB that we end up designing for the group. We also ran into a few minor issues on this side. Specifically, here we can see that we had to incorporate a bunch of extra GPIOs, and that happened because it turns out we were missing quite a bit of pins for the display. So we had to solder a bunch of extra wires to GPIOs. All of those wires are going to just extra GPIOs soldered to pin headers so that we can use more additional pins for the display. Some of the changes that occurred on this PCB was we swapped out the switch-in regulator and we used another linear regulators because we knew those worked. And we also updated the circuit that we had issues prior, and we made that correction, as we can see over here. So now we were able to effectively create a circuit that was wired correctly, and then we're able to boot up the chip. In terms of a demonstration, you can see that working. Once we go over here, we upload the code, and then we try to compile it. I would do the same thing that I did on the previous one. Reset boot, and that should give me a full compile. And here we see that everything is running successfully, and we're able to fully boot up the chip. In terms of design, everything else was remained the same. We didn't really change much else because since we were actually able to get the first board up and running, I figured we kept the design the same, and we just tweaked the areas that needed a tweaking, which were the switching regulators and rerouting the trace that went to the pull-up resistor button, and making sure we fix those critical points. Thank you.